In this video, we're going to look at graphing functions using calculus. I have a little mnemonic that I use to help remember all of the information that we're going to find before we graph the function. I use ICL2Cs, and you may want to pause the video and write some of this down, but we're going to go through this rather quickly. Most of this we've covered already, so you should have a familiarity with this. First of all, intercepts, and then to determine symmetry, to find asymptotes, our intervals of increase and decrease, our local maximum and local minimums, a continuation of our local maximum and minimums, now this is using the second derivative test. We have two different ways of identifying local maximum and minimums. Domain, then we can determine the intervals of concavity, and then we can sketch the graph. So let's take a look at an example. Here we have, for the following functions, find the domain, intercepts, symmetry, intervals of increase, decrease, local max and mins, concavity and points of inflection. Then sketch the curve without a calculator. I encourage you to do this without looking at the function before you try to sketch the graph. It is a little bit challenging, but you'll get much better at this much quicker if you don't look at the function first before you try to graph it. So we're going to look at graphing y equals 2x squared divided by x squared minus 1 using calculus. So let's look at our tests. So we will write our function here. We're working with f of x equals 2x squared all over x squared minus 1. So first of all, we're going to be looking at, remember I use this ICL to C's. So the first I represents our intercepts. So to find our x-intercepts, we would let y equal 0. So we'd have 0 equals 2x squared divided by x squared minus 1. And we know this rational expression only equals 0 when the numerator equals 0. So we would have x equals 0. So there is an x-intercept. And we'll notice or keep in mind that this intercept has a multiplicity of 2. Let's find our y-intercept. To to find our y-intercepts, we let x equals 0. So if we plugged in 0 to our function, we'd have y equals 2 times 0 squared is 0, all over 0 minus 1. So we'd have a y-intercept at 0, 0. So there's the first test, I. S stands for symmetry. So let's look at the symmetry of this graph, if it has any. So to determine symmetry, we plug in a negative x to our function, and then even powers we rewrite like this. And you can refer back to the sheet that I displayed in the first part of this video for symmetry. That explains what happened in that step. Now this does equal our f of x. So we have f of negative x equals f of x, because this right here, what we got from plugging in a negative x into our function and simplifying it, we plugged in a negative x and we got the function back itself. So that tells us this function is even. Therefore, this has symmetry with respect to the y-axis. So we have our symmetry. Now A. A, we are looking for any of our asymptotes. So I believe we're going to have to create a new sheet. So we have our function 2x squared all over x squared minus 1. And now we're going to be looking for asymptotes. So the way we determine if we have any asymptotes, we take the limit of our function as x goes to infinity, and we also have to check negative infinity. Now if we use direct substitution, we would get infinity over infinity, so we can apply L'Hopital's rule. So we would get the limit of 4x all over 2x. And if we use direct substitution, again we would get infinity over infinity. So we can apply L'Hopital's rule again. And this limit equals 2. Now we have several techniques that allow us to find this limit, but this is just one way using L'Hopital's rule. We also have to check the limit of our function as x approaches negative infinity. Now if we plugged in negative infinity, we would again get infinity divided by infinity. So we can apply L'Hopital's rule. And again, applying L'Hopital's rule, and we can now use direct substitution or simplify before we use the substitution. So here, if we applied L'Hopital's rule again, because we get infinity over infinity, we would get 4 divided by 2. So we do have a horizontal asymptote as x goes to infinity at y equals 2. That would be the equation of the asymptote. And we have a horizontal asymptote as x goes to negative infinity. So we have done our intercepts, we've done our symmetry, we've looked at our asymptotes. Now we're going to look at our intervals of increase and decrease. To find our interval of increase and decrease, we need our first derivative. If we looked at the derivative, we would have the bottom times the derivative of the numerator minus the top times the derivative of the denominator all over the denominator squared. And when we simplified this, we would see that our derivative simplifies to negative 4x all over x squared minus 1 squared. Now the test for increase and decrease, we set our derivative equal to 0. We have to determine where a derivative equals 0. We also have to determine if there are any values of x that make the derivative undefined or where it does not exist. First off, let's set our derivative equal to 0. And here we see that if we set the numerator equal to 0, we get a critical number at x equals 0. There's our critical number from setting the derivative equal to 0. Now we have to determine, does the derivative not exist for any values of x? So if we set the denominator equal to 0, that will give us any place where the derivative does not exist. That's what we're looking for here now. So if we set this equal to 0, we could square root both sides, but we'd still have 0 on the right-hand side. And then we could solve for x, so we would have plus or minus 1. So we have two critical numbers from where the derivative does not exist. So altogether we have a critical number at 0, and we have a critical number at negative 1 and a critical number at positive 1. So if we draw a number line and we put our critical numbers on our number line, we want to check each one of these intervals. negative infinity to negative 1, negative 1 to 0, 0 to 1, and then 1 to infinity. So we have these four intervals to check for increase and decrease. So we choose any value on that interval and plug it back into the derivative. So I'll take negative 2. Now I like to look at the derivative. Here I'm going to look at the derivative here, and I can see that no matter what I plug into the denominator is always going to be positive since it's being squared. So I see a positive number always coming out of the denominator. Now if I plug negative 2 into the numerator, I get negative 4 times negative 2 is positive 8. So I would have a positive divided by a positive gives me a positive value. So we know it is increasing on this interval, negative infinity to negative 1. Let's choose a value to plug in between negative 1 and 0. So I'm going to choose negative 1/2. And again, we're just going to use our derivative to determine if it's positive or negative. We know the denominator is always negative. If we plugged a negative 1/2 into the numerator, we'd get a positive value. So again, it's increasing on this interval from negative 1 to 0. Let's plug in 1/2 on this interval. And we can see that in the numerator, we're going to have a negative value this time, because negative 4 times 1/2 would give us a negative value. Therefore, a negative divided by a positive gives us a negative value. So we would be decreasing on this interval. And the last interval, f prime, let's choose 2. And again, if we plug 2 into our function, the denominator is going to give us a positive value. But if we plug 2 into the numerator, we get negative 8. So it again is going to be decreasing on this interval from 1 to infinity. So there's our test for increase and decrease, where our function increases, where our function decreases. Now we can do the next test right from the information we received from this test. We're going to look for local max and mins. Now we know a local max or min arises when at a critical number, if the function changes from increasing to decreasing or decreasing to increasing, we could have a local max or min. At negative 1, it's increasing and then it stays increasing, so there's no local max or min there. But at 0, we see here at 0 that it's increasing, but then it changes to decreasing. So we would have a local maximum. And then at positive 1, decreasing, stays decreasing, so we won't have a local max or min there. So there's our test for increasing and decreasing and our local max and mins. Now the domain of this function, we can see the domain of the original function here, our original function. The domain is going to be, let me clear just a little bit of room up here for this. So our domain, we would have to eliminate the values 1 and negative 1 because those values would make the denominator equal 0. So our domain would be from negative infinity to negative 1, and then negative 1 to 1, and then to eliminate 1, we'd go from 1 to infinity. So that's going to eliminate our values of x that make this function undefined. So we know that x cannot equal positive or negative 1. All the other values of x are in the domain of this function. Our last test, so we've done our domain. Now the next test is for concavity. So let's take a look at, let's rewrite our function. We have 2x squared all over x squared minus 1. We have already found the first derivative. We know for concavity we're going to look at our second derivative. This is our first derivative, x squared minus 1 squared. Now we would have to apply the quotient rule to find our second derivative. So we'd have the bottom times the derivative of the top minus the top times the derivative of the denominator, which would be 2 times x squared minus 1, subtract 1 from the exponent. But in applying the chain rule, we'd have times 2x, the derivative of the inside function, all divided by x squared minus 1. This quantity would be squared. This is a 2 here also. So if we simplified this, we would get 12x squared plus 4 all divided by x squared minus 1 cubed. And the easiest way to simplify it is pull out your common factors in the numerator, which would be your x squared minus 1, and you could also, it looks like, pull out a 4x or a negative 4x, and then simplify it from there. Now, to find the possible points of inflection, we're going to set our second derivative equal to 0. And we're also going to look where it is undefined, because it could change concavity at those points also. So if we set our second derivative equal to 0, again, we only have to set the numerator equal to 0, because we could say we're going to multiply both sides by x squared minus 1 cubed. That would go to 0 on the left side, or the right side in this case. And then if we tried to solve this, can you see that if we subtract 4 and then divide by positive 12, we can't take the square root of a negative number and get a real number. So this is not going to give us any possible points of inflection. So second, we have to determine if there are any values of x where the second derivative does not exist. So we would set the denominator equal to 0. We would take the cube root of both sides. We'd get x squared minus 1 equals 0. And if we solved for x here, we would get positive and negative 1. So building our intervals from those possible points of inflection. And this time we're going to plug our values into the second derivative to determine concavity. But I'm going to use the same technique as what we did with the first derivative test. I'm just going to determine if we have positive or negative values. Now let me write the intervals here above. Our intervals would be from negative infinity to negative 1, from negative 1 to 1, then our last interval would be from 1 to infinity. So now we can plug a value. Let me choose, let's see, negative 2. So going back to our second derivative, if we plug in negative 2 into the numerator, now we're using this right here. If we plugged in negative 2 to the numerator, you can see we'd square negative 2 to get 24 plus 4. It would give us a positive number. Now in the denominator, if we plug negative 2, we would get negative 2 squared is 4, 4 minus 1 is 3, 3 cubed, 27, positive number. So this tells us that we are concave upward on this interval. If we plugged in 0, so let's determine if the second derivative is positive or negative at 0. At 0, we would get positive 4 in the numerator, and then negative 1 cubed in the denominator would be negative, so a positive divided by a negative would give us a negative value. So on this interval, we are concave downward. The last interval, I'll choose 2. And again, the numerator is always positive. And then the denominator, we would plug in 2. We'd have 4 minus 1 is 3, 3 cubed. We would get a positive divided by a positive. So we will be concave upward on this interval. Now we have all of our tests. The last thing that we need to do is put this all together and graph the function. Let's close this one out. So let's see if we can get a split screen here so we can go back over our tests. So now we're going to try to graph our function using these tests that we've just found. So let's go back. I like to graph my intercepts first. So we have our, let's move this down. See if we can move this out of the way here. So we have our intercepts. We have our intercepts at 0, and we said that has a multiplicity of 2. So we know that at 0, let's see, that's not letting me draw, so let's let's graph this on, let's see if we can get this onto another graph. Okay. So if we looked at our information now, we said we had intercepts at 0, x-intercepts at 0, and it has a multiplicity of 2. So let's put our x-intercept here at 0, 0. Let's say this is 1, 2, 3, negative 1, negative 2, negative 3. And we have a multiplicity of 2, so we know it's going to bounce. We don't know yet if it's going to come from beneath, up, and bounce back down, or come from the positive x values or positive y values and bounce back up. But we know we have an x-intercept at 0, 0. Next, let's see if we can our asymptotes. We have an asymptote, a horizontal asymptote at y equals 2. And also we didn't check for our vertical asymptotes. We know vertical asymptotes would come from if you set the denominator equal to 0. So we'd have vertical asymptotes at plus and minus 1. So if we plotted those, let's plot our vertical asymptote at negative 1 and positive 1. And we said we have a horizontal asymptote at 2. So we have our asymptotes drawn in. Next, we looked at our intervals of increase and decrease. So here we can see that from negative infinity to negative 1, we're increasing. 1 to 0, we're increasing. And from 0 to 1, we're decreasing. And from 1 to infinity, we are decreasing. So let's just draw those in. And also we have a local maximum at 0. So we'll remember to draw that in also, local maximum. But let's just draw in on our graph now. We don't know exactly where the function is, but if we think through this, coming from negative infinity up to negative 1, if we're increasing, we can't be down in this area, because if we were increasing from negative infinity to negative 1, then we would have to have an x-intercept. Now we don't have an x-intercept through there, so we would need to be up in this area above the horizontal asymptote. So we're going to be up in this area. So we're going to be increasing. So we would be coming from, now this horizontal asymptote would be coming from that horizontal asymptote. Let me put this in a different color. We would be coming from here and moving towards that vertical asymptote. And I'm just going to write if we're increasing or decreasing. We're not going to look at concavity yet. We'll do that since we can't see it all at the same time. Now from 1 to 0 it says we are increasing also. But we do have an x-intercept at 0, 0. So we would have to be down here increasing if we have an x-intercept at 0, 0. And from 0 to 1 we are decreasing. And this makes sense because we have an x-intercept at 0, 0, and we know it has a multiplicity of 2, so we said, well, we know it has to bounce, come back down, and this indicates that we're decreasing. And then on the interval 1 to infinity, we are decreasing. And again, we can't be down in this area here, anywhere down here, because if we were decreasing, we would have to start up in this area and then cross the x-axis, but we don't. So that would indicate that we have to be above our horizontal asymptote. So we would have to be up here and decreasing, and then we would be approaching our horizontal asymptote. And just as a reminder of what we found earlier, it did say we had symmetry, and the symmetry was with respect to the y-axis. All right, so let's now look at our concavity. So if we go back to our concavity, here we have from negative infinity to negative 1, we're concave upward. From negative 1 to 1, we're concave downward. And from 1 to infinity, we're concave upward again. So let's go back to our graph. Now we can apply our concavity. So from negative infinity to negative 1, we are increasing concave upward. So let's draw that in. Increasing concave upward. Let me extend our asymptote. So let's erase this now that we know about the concavity. So we would be increasing concave upward. So we would have to be doing this, and then we're going to be approaching this asymptote. Now from negative 1 to 0, we were increasing, and from negative 1 to 0, we are concave downward. So here we could draw in our, we know we're concave downward there, so we can draw that in. So increasing concave downward, and we know there's an x-intercept at 0, 0. And from 0 to 1, we're decreasing. and our concavity is still down. So we would draw our graph now. We would say decreasing concave downward, and then we would be approaching our asymptote. And then on the interval from 1 to infinity, we're decreasing but concave upward. So if we draw that in, decreasing concave upward, we're going to be approaching our asymptotes. And we can see the symmetry that we found with respect to the y-axis. And looking at our domain, we said our domain, we had to remove the points -1 and 1, and we can see from this graph those have been removed. So that's how we use all of our tests to determine what the graph looks like, just using our calculus.